Tonight we are going to follow something almost no one has imagined properly. The closest other star to our Sun is called Alpha Centauri. It is 4¼ light-years away, 25 trillion miles. One of humanity's farthest spacecraft, Voyager One, has been flying since 1977. In November of 2026, that spacecraft finally reached a distance of 1 light day from Earth. It took 49 years. At that same speed, reaching Alpha Centauri would take roughly 70,000 years. But there is a small group of scientists who have been working since 2016 on a way to do it in 20. Their plan does not involve a starship. It involves a fingernail. A chip of metal weighing 1 gram, with a tiny sail and a tiny camera, pushed for 10 minutes by a laser the size of a small city, then abandoned to 20 years of empty space. If you find yourself drawn to these kinds of journeys, the ones that ask quietly what it would actually cost to leave home, take a moment to like the video and subscribe. It helps this channel keep walking these long roads with you. Now, settle in. Let your shoulders drop. We begin. It is somewhere in the middle of the 21st century. The exact year does not matter for our story. What matters is that the laser array has been built. It sits on a high plateau, somewhere with thin air and clear skies. Chile, perhaps, or western China, or the high deserts of New Mexico. The specific location is a question engineers are still arguing about as we speak. What is not in question in our story is the array itself. It covers several kilometers of ground. It looks, from above, like a great honeycomb of mirrors and emitters, each one tied into a control system that synchronizes them all to within a fraction of a wavelength. Together, they can produce a beam of light measured in gigawatts. That is roughly the output of a large nuclear power station, focused into a single column of coherent light aimed straight up. Above the array, far above the atmosphere, a small mothercraft is in orbit. It is not very large, about the size of a refrigerator. Inside it, packed in a careful cradle, there is a stack of small flat squares. Each square is about 10 meters across when unfolded. Each is no thicker than about 100 atoms. The material itself is something engineers have been refining for decades by this point. Graphene compounds, photonic crystals, materials with names that did not exist when you and I were born. The sails are folded down to fit inside the mother craft, but in space, when the time comes, they will open like flowers. At the center of each sail, there is something even smaller. A chip, about the size of a postage stamp, weighing less than a gram. Inside that chip, there is a small camera, a small computer, a tiny battery powered by the slow decay of a radioactive element, and a small communications laser. The laser on the chip is rated at 1 watt, about the same as a bright kitchen light bulb. The chip is the entire spacecraft. There is no crew compartment, there is no engine, there are no maneuvering thrusters. There is the chip, and there is the sail. That is all. Down on the ground, in a control room not far from the laser array, a small team of people is watching screens. They are not many, a few dozen perhaps. The original founders of this project, 2 men named Yuri Milner and Stephen Hawking, both announced the program in 2016. Hawking has been gone for years by this point. Milner is elderly now, watching from somewhere, perhaps still in attendance, perhaps not. The project has changed hands several times. There are people in this control room tonight who were children when the announcement was made. There are people in this control room tonight who were not even born then. That is the strange thing about projects that span longer than a career. They belong to many people in sequence. No single person can own them. The mothercraft above the atmosphere releases one of the sails. The sail unfolds. The chip is attached to the center, where the sail meets a small frame. The whole assembly, sail and chip, weighs only a few grams in total. It drifts for a moment in the vacuum above the Earth, catching faint starlight on its mirrored surface. It looks, for that one quiet moment, like a piece of jewelry hanging in space. Then the laser fires. We will not be able to see this from the ground. Not properly. The beam is too tight, too narrow, to leave a visible trace in the air. But the energy it delivers is real. For 10 minutes, a column of gigawatt-class light pushes against the sail. The pressure of light is something most people never think about, because in everyday life, light has no weight you can feel. But at gigawatt intensities, focused onto a sail that is almost weightless, the pressure is enough to accelerate the chip at thousands of times the force of Earth's gravity. The numbers depend on the exact design, but the acceleration is somewhere on the order of 10,000 g. To put that in scale, a fighter pilot in a tight turn experiences about 9 g, briefly. After 10 g, untrained humans lose consciousness. At 100 g, a human body breaks. At 10,000 g, a human body is not even a body anymore. It is a stain. This is why the probe weighs a gram. This is why the probe is a chip and not a ship. Only things without bodies can take this acceleration. Only things without lungs, without blood, without the long, delicate plumbing of a living animal can endure the moment of the laser. The chip is built of solid-state components. Silicon. Metal oxides. Materials that, at their scale, simply do not care about 10,000 g the way a heart does. For 10 minutes, the chip and its sail are pushed. The chip cannot feel anything. It has no nerves. But it is being changed. With every second, it is faster than it was the second before. After 1 minute, it is moving at roughly 1% of the speed of light. After 3 minutes, it is at 5%. After 8 minutes, it is at 15%. After 10 minutes, the laser shuts off. The chip is now moving at 1/5 of the speed of light, roughly 60,000 kilometers every second. That is faster than anything humanity has ever built. That is faster than anything humans had ever imagined building until quite recently. That is fast enough to cross the entire distance from the Earth to the Moon in a little over 6 seconds. And now the laser is off. The chip is alone. It will not be pushed again. It will not be slowed. It will not be turned. From this moment on, for the rest of its existence, the chip is in pure ballistic flight. It is a bullet, the most expensive bullet ever fired by humans. And the target is 25 trillion miles away. Down in the control room, the team watches the telemetry confirm the burn. The numbers come up clean. The sail has held. The chip has reached the planned velocity. There is applause. There are tears in some of the eyes. Some of these people have worked on this single moment for 30 years. Some of them came in as graduate students. Some of them were senior when they joined and are senior still, but quieter. They cannot follow the chip. No one can. The chip has already crossed several hundred kilometers of space in the time it took them to stand up from their chairs. The next probe goes out 2 nights later. Then another. Then another. The plan is to send many, possibly thousands. Knowing most will fail. Some will be hit by debris before they leave Earth's neighborhood. Some will tear their sails during the laser burn. Some will simply drift off course and miss the destination. The whole strategy depends on numbers. Send enough and a few will arrive. Send enough and the universe will eventually let 1 or 2 slip through. But our story is about one chip in particular. The first one, the one that flew clean. Tonight we are going to follow that chip across 24 years. We are going to see what the journey looks like year by year. We are going to watch what it does to the chip, what it does to the sail, what it does to the people on the ground who are waiting. We are going to walk the long road between here and there, slowly, in the dark, the way that road must be walked. because no matter how fast the chip moves, the road is still mostly empty. And no matter how clever the engineering, the chip is still alone. Settle in. The laser has stopped firing. The chip has begun its journey. The voyage to Alpha Centauri has finally, after all the talk and the plans and the papers and the arguments, begun. Let us pause for a moment, here at the start, and stay with that 10-minute window, because the entire rest of this story depends on what happens or fails to happen in those 10 minutes. After the laser shuts off, nothing can be fixed. There are no thrusters on the chip. There is no way for the team on the ground to nudge the trajectory. There is no way to slow it down if it is going too fast, or speed it up if it is going too slow. Whatever the chip is doing at minute 10 is what it will be doing for the next 20 years. The 10 minutes is the entire mission, in a sense. Everything else is consequence. Imagine for a moment what is actually happening to the sail during those 10 minutes. The laser is hitting it with a column of light so intense that, if you stood in that beam yourself, even for a fraction of a second, you would not survive. The sail is a thin, almost transparent thing. It is mostly empty space at the molecular level. The whole point of its design is that almost all of the light bounces off, because the more light bounces off, the more the sail is pushed forward. If even a small fraction of the light is absorbed instead of reflected, that fraction becomes heat, and heat at these intensities can vaporize the sail in milliseconds. This is one of the reasons the project took so long to be taken seriously. Even in the years just after the announcement in 2016, there were respected physicists who said that no sail could survive a gigawatt-class beam. The math, they argued, simply did not work. You could not make a material that was light enough to be pushed and tough enough not to burn, both at once. Either the sail would be too heavy and the chip would never reach the required speed, or the sail would be too thin and the first instant of the laser burn would turn it to ash. A great deal of the engineering work in the years after the announcement was about this single problem. Teams at Caltech, at Harvard, at the Max Planck Institute in Germany, at Queen Mary University in London. Materials scientists testing photonic crystal designs. Optics engineers building prototype emitters. Physicists running computer simulations of how a sail would deform under thrust, how it would oscillate, how it might tear. The published papers piled up. The funding came in small amounts, then larger amounts, then very large amounts. By the late 2030s, the basic problem was understood. By the 2040s, prototype sails had been tested in laboratory vacuum chambers under scaled-down beams. By the time, in our story, that the chip actually flies, the engineering is mature. The sails work, most of them, most of the time. But not all of them, not all the time. This is something we should be honest about. The chip we are following, the one that flew clean, is not the only chip launched that night. It is one of several. Some of the others tore. We can imagine, if we want, what that looked like. The sail at the start of the burn, perfectly flat, catching the column of light. Then a small flutter at one edge, perhaps from a microscopic defect in the material. Then the flutter growing. Then a single tear, propagating across the surface like a crack across a windshield. Then the sail folding in on itself. Then the chip, no longer being pushed evenly, tumbling, spinning, losing its grip on the beam. Then drifting away in a wrong direction, at a wrong speed, into the dark. The chip is still functional in those moments. The little camera is still on. The little computer is still running. But the mission is gone. There is no recovery. There is no rescue. The chip will drift on whatever trajectory the tearing imparted for some uncountable amount of time, going slowly nowhere. This is why thousands of probes will be sent over many years, knowing most will fail. The strategy is volume. If 1 in 1,000 makes it through the launch cleanly, and 1 in 1,000 of those survives the journey, and 1 in 1,000 of those is pointed in the right direction at the end, you still have, on average, 1 chip arriving for every million launched. That is the cost of a project like this, not in money, but in failed copies of itself. Take a breath, settle back. The journey is long, and we have only just begun. The chip we are following is one of the few that survived its first 10 minutes. The sail held. The acceleration was even. The trajectory came out clean. By the time the laser shuts off, the chip is already several thousand kilometers above the Earth, moving outward at a speed that the human mind does not really know how to picture. 60,000 kilometers per second is not a number you can feel. It is not a number you can intuit. The best way to get any sense of it at all is to compare it to other things. If the chip were moving over the surface of the Earth at this speed, instead of away from it, it would cross from one side of the planet to the other in 0.2 of a second. The whole of the Pacific Ocean would pass beneath it in less than 1/5 of a second. A flight from New York to Tokyo, which takes a commercial airliner about 14 hours, would take this chip about 0.2 of a second. From Earth to the Moon, 400,000 kilometers, would take about 6.5 seconds. The chip would be at the Moon before you finished a slow breath in. Of course, the chip is not going to the Moon. The chip is going to a place that is roughly 100 million times further than the Moon. At this speed, the journey to the Moon is 6 seconds. The journey to Alpha Centauri is 20 years. The ratio between those two numbers tells you something about how unimaginably far the closest other star really is. Down in the control room, in the hour after the burn, the team is doing what teams have always done after launches. They are running diagnostics. They are checking telemetry. They are confirming over and over that the chip is on course. The first signals from the chip itself, after the laser shuts off, take about 1/100th of a second to arrive. By the next day, the signal delay has grown to about 1/10th of a second. Within a week, the chip is far enough away that any message takes several seconds to come back. Within a month, several minutes. Within a year, the signal delay will be measured in hours. By the time the chip reaches its destination, 20 years from now, the delay will be over 4 years long. This is something the team understands intellectually, but understanding it intellectually and feeling it are different things. The chip is now beyond their reach. Not just physically, it is beyond their conversation. Whatever instructions they may have wanted to send, they sent before the burn. Whatever code they wanted on board, they uploaded before the burn. There is no opportunity to fix bugs in flight. There is no opportunity to add new instruments. The chip is, from this moment on, sealed. It will do what it was told to do, and only that, until either its battery runs out or some grain of interstellar dust ends its journey early. Many of the people in the control room are, by their own admission, exhausted. Some of them have not slept properly in days. Some of them have been working on this single launch for years. There is the strange, slightly hollow feeling that follows any big launch. The thing you have been preparing for is over. The thing you cared about is now beyond your reach. And the work is, in a sense, only just beginning, because now there will be 20 years of waiting, watching, listening, and praying that the chip does not die on the way. By the end of the first day, the chip is far past the Moon. By the end of the first week, it has crossed the orbit of Mars. By the end of the first month, it is approaching the orbit of Jupiter. By the end of the first 3 months, it is past the orbit of Saturn. By the end of the first 6 months, it is past Neptune, past Pluto, past the outermost edge of what most people think of when they think of the solar system, and the chip has not yet completed 1 full year of its journey. This is the thing we have to keep reminding ourselves throughout the story. The chip is moving very, very fast, but the distance is so much greater than the speed that even moving at 1/5 the speed of light, the journey will still take 20 years. The chip cannot rush this. The chip cannot cheat the distance. The chip can only fly. And the distance, like all distances in space, must be earned 1 kilometer at a time. For most of the first year of the chip's journey, the people on Earth can still pretend, in some small way, that the chip is close. The signal delay is measured in hours, not years. The position of the chip can be plotted on a chart of the solar system, and it still appears, on those charts, as something inside the local neighborhood. The chip is inside the territory we have mapped. The chip is, for a few months yet, in the same sky we have been looking at all our lives. But the chip is moving very quickly through that territory. By the 3rd month of the journey, the chip passes the orbit of Saturn. Saturn is one of the planets that most of us have at least a vague picture of. The rings, the pale yellow color. The Cassini mission spent 13 years exploring it and ended in 2017 by deliberately diving into the planet's atmosphere. By the time our chip crosses Saturn's orbit, almost no one alive remembers Cassini directly. The mission belongs to history now, the way the Apollo program already belonged to history when many of us were children. The chip flies past the place where Saturn happens to be, or where Saturn happens not to be that month, because Saturn is also moving on its own slow path around the Sun. The chip does not stop to look. The chip cannot stop. The chip is on a straight line. By the 6th month, the chip is past Uranus and Neptune, past the orbit of the last big planet. By the end of the 1st year, the chip is somewhere out in the region that astronomers call the Kuiper Belt. This is a region of icy bodies, comets, dwarf planets like Pluto, and uncountable smaller objects. The Kuiper Belt is one of those names that sounds, when you hear it on a documentary, like a coherent thing. A belt, a defined region. In reality, the Kuiper Belt is so sparse that the chip is unlikely to come anywhere near any of its objects. The chance of a random collision is extremely small. The chance of a useful encounter is also small. The chip is just passing through. By this point, the chip has covered roughly 1 light week of distance from Earth. A light week is the distance that light travels in a week, about 180 billion kilometers. In our solar system, that is a long way. From the perspective of the chip's mission, it is a tiny fraction of the total journey. The chip is about 1 part in 1,000 of the way to its destination. 99.9% of the road still lies ahead. But here is the comparison that begins to land. There is another spacecraft out in the same region of space, not very far from the chip, in cosmic terms. It is called Voyager One. It was launched in 1977. It has been flying outward for 49 years by the time our chip is launched. In November of 2026, Voyager 1 reached a distance of 1 light day from Earth. That is, the distance that light covers in 24 hours. 16 billion miles. 26 billion kilometers. For Voyager 1, that was a milestone of nearly half a century of patient flight. For our chip, the same distance is crossed in about 5.5 hours. 5.5 hours. Sit with that for a moment. The farthest object humanity ever sent into the dark before this chip took 49 years to reach a distance that the chip covers in less time than a long working day. By the end of year 1, the chip is roughly 1,700 times further from Earth than Voyager. One was at its launch milestone in 2026. The chip is sailing past Voyager 1 in a sense, somewhere far out in the dark, although the two are not actually near each other. They are on different trajectories, aimed at different parts of the sky. But the comparison still holds in feeling. The farthest thing we ever sent before this is being lapped by something smaller than a coin. This is, in some ways, the strangest part of the chip's journey. Year 1 is the year when the chip is still in our neighborhood. Year 1 is the year when the chip crosses, in a few months, the territory that took our previous spacecraft decades. Year 1 is the year when, if anyone is going to understand viscerally how fast this thing is moving, it has to be now. Because after Year 1, all of the comparisons stop mattering. After Year 1, the chip is in interstellar space proper, and the only thing left to compare it to is the speed of light itself. Take a breath. The chip is moving. It is still moving. It has not stopped, and it will not. Down in the control room, the team has, by the end of Year 1, mostly dispersed. The launch crew has handed the project over to a long-term operations team. Some of the senior engineers have retired. A few of them have moved on to other projects, including the development of newer probes for other star systems, projects that will not be launched until decades from now. The mission is, by Year 1, a stable thing. A thing that runs in the background of Earth's scientific institutions, monitored by a small group of dedicated specialists, with occasional updates published in journals and occasional press releases issued on anniversaries. There is a particular kind of person who works on these long missions. NASA has them on the Voyager team. The current Voyager operations team includes retirees in their 80s who advise on specific subsystems, and team members so young that even their parents were not born when the Voyager probes lifted off in 1977. That intergenerational mixture, the senior advisors and the young engineers, is what allows a mission to survive across human time spans. The same will be true for our CHIPS mission. The people who watch it in Year 1 will not be the people who watch it in Year 20. But there will be continuity. There will be handoffs. The knowledge will be transferred, slowly, from one set of careers to the next. Inside the chip itself, by Year 1, the small radioactive battery has decayed slightly. Not much. Its half-life is many decades. But the chip is now running on slightly less power than it had at launch. The little camera has not been used yet. The little computer is running its main monitoring program, recording the slow trickle of cosmic ray hits, the gradual change in the magnetic field, the very faint pings of dust grains striking the sail. These signals, when they are transmitted back to Earth at the chip's 1 watt of communication power, will eventually be assembled by scientists into a picture of what the local interstellar medium really looks like, not in computer simulation, in direct measurement, from inside. This is, by the way, one of the reasons projects like this matter. We have many predictions, from theory and from indirect observation, about what the space between stars contains. We have measurements from the Voyager probes, which crossed into interstellar space in 2012 and 2018. But Voyager One is moving slowly, by the standards we are talking about now. Our chip is moving 3,500 times faster. The kind of measurements the chip can make, even with a 1-gram payload, are measurements no previous human instrument has been able to make. It is, in that sense, a scientifically useful probe, even before it arrives anywhere. The journey itself is the data. The journey itself is the discovery. By the end of Year 1, the chip is somewhere around 12 billion kilometers from Earth, give or take. Its signal, transmitted from a 1-watt laser, takes about 11 hours to reach the antennas waiting on the ground. The antennas are large. They have to be. To catch a 1-watt whisper from 12 billion kilometers away, you need a receiver the size of a city block, pointed very precisely, integrating the signal over many seconds. That kind of receiver is expensive. It draws power. It requires staffing. It can only listen to one chip at a time. The economics of listening to a swarm of chips is its own engineering problem, and one that the project has been quietly solving in the background for years. But for now, in our story, the receiver works. The signals come through. The chip is silent for most of every day, conserving battery, but once every few hours it sends a small packet of data, a handful of bytes, a status report. The numbers it sends back are the numbers of an instrument that is functioning. Battery within nominal range. Sail intact. Cameras nominal. Computer functioning. Trajectory on course. By the end of year 1, the chip has produced more data in terms of distance covered per second of measurement than any human probe before it. And the chip is still very, very far from where it is going. In year 2 of the chip's journey, something quietly important happens. The chip leaves the heliosphere. The heliosphere is the bubble of charged particles that the Sun blows out around itself. It extends, very roughly, to about 120 times the distance from the Earth to the Sun. That is the rough boundary where the wind from our star runs out of pressure and meets the much fainter wind that flows between the stars. When Voyager One crossed this boundary in 2012, it was, in a real sense, the first human-made object to enter interstellar space. The headlines at the time called it a milestone. It was. It is. And by year 2 of our chip's journey, the chip has crossed that same boundary. For Voyager 1, getting to that boundary took 35 years. For our chip, it has taken about 2. The same threshold, crossed 17 times faster. The chip is now in the place where Voyager has been since 2012. The chip is now in the place where, until recently in human history, no built thing had ever been. But here is the catch. The interstellar space the chip enters is not empty. It only seems empty. The region of space immediately around our solar system is called the local interstellar cloud. It is a diffuse cloud of gas and dust, roughly 30 light-years across. Our solar system has been drifting through it for tens of thousands of years. We will continue to drift through it for tens of thousands more. The local interstellar cloud is, by the standards of clouds we know on Earth, almost unimaginably thin. The air in your bedroom contains roughly 27,000 million molecules per cubic centimeter. That is a number with 20 zeros. The local interstellar cloud contains, on average, about 1/10 of 1 atom per cubic centimeter. 1/10 of 1 atom per cubic centimeter. This means that in a volume the size of a small room, in the local interstellar cloud, there are roughly 25,000 hydrogen atoms. Less than the air in a single breath, spread across an entire room. Less than a single dust mote, spread across a hangar. The local interstellar cloud is, by any human standard, empty. And yet the chip is moving through it at 60,000 kilometers per second. This is where the first real damage begins. Because at 1/5 the speed of light, even a single hydrogen atom is no longer a peaceful neighbor. At that speed, a hydrogen atom hitting the sail is not gas. It is radiation. It penetrates the sail. It deposits its tiny pulse of energy. It moves on. Over a single second of travel, the chip sweeps through enough cubic centimeters of the local interstellar cloud to encounter, on average, somewhere on the order of millions of hydrogen atoms striking its frontal area. None of those atoms, individually, is enough to harm the chip, but cumulatively, over years, they begin to wear away at the sail. They chip away at the chip itself, very slowly, atom by atom. There is also the dust. The local interstellar cloud contains, by mass, about 1% dust. Tiny grains of carbon, silicates, ice, metals. Most of them are smaller than the wavelength of visible light. Most of them are too small to see in any normal sense. But at 60,000 kilometers per second, even these tiny grains carry kinetic energy. The smallest dust grain, the kind that floats invisibly in the cloud, hits the sail with the energy of a small bullet in the moment of impact. The sail is designed to take such hits. It can absorb a great many of them, but not without cost. Each hit leaves a tiny pinprick of damage, a pinprick that does not heal, a pinprick that adds to thousands and thousands more pinpricks over the years of the journey. The breakthrough starshot studies, going back to the 2010s, estimated that the chip's frontal area would be struck during its journey by approximately 1,000 particles of size 1/10 of a micrometer or larger per square centimeter. That is 1,000 visible scale dust hits on every patch of the chip the size of a fingernail over 20 years. The cumulative effect is that the sail, by the end of the journey, will not be the bright, clean, reflective surface it was at launch. It will be pocked, pitted, slightly torn in places, still functional, almost certainly, but aged. The chip's first journey is also its only journey. There is a paper written in 2007 by two astronomers named René Heller and Michael Hipke, working at the Max Planck Institute for Solar System Research. They proposed an extension of the breakthrough starshot concept. Their suggestion was that, at the destination, the same kind of sail could be used in reverse. By rotating the sail to face the light of Alpha Centauri itself, and by using a sail much larger than the one used for acceleration, the chip could in theory use the photons from the destination star to decelerate. They called the technique photogravitational assist. Under their proposal, a probe could in principle arrive at Alpha Centauri and then continue more slowly into the system around Alpha Centauri A and B, and eventually settle into orbit around Proxima Centauri. The journey time would be longer, perhaps 75 years instead of 20, but the chip would actually arrive rather than only passing through. This is a fascinating proposal. It exists. It is in the literature. It has been studied by other physicists. But the current design of the chip we are following does not include it. Our chip is a flyby probe. It will not slow down. It will not stop. It will pass through the Alpha Centauri system at full speed. Whatever data it can collect, it will collect in the seconds when the planet is in range. After that, the chip continues on into the far side of the system and onward into the deep dark of the galaxy beyond. Take a breath. Let your shoulders drop. The chip is alone, but it is on the right path. By year 3, the chip is roughly half a light year out. The Sun, looked at from the chip's position, is no longer a disk you could resolve with the naked eye. It is one of the brighter stars in the sky, viewed from out there, but it is just a star. It is not warmer than the others. It is not larger. It is one point of light in a sky full of points. From the chip's perspective, if the chip had a perspective, the Sun has become, in 3 years, just another star. By year 4, the chip is roughly 1 light year out. The chip is, by this point, deeper into interstellar space than any human spacecraft has ever been or will ever be for many decades to come. The chip is alone in a way that no probe before it has been alone. There is no Voyager nearby. There is no Pioneer to compare with. The chip is opening a new region of the human map. By year 5, the chip is more than a light year and a half from Earth. The chip is now more than a third of the way to its destination. The chip has, for the first time, crossed a threshold where the time it takes the chip's signal to reach Earth is measurable in years, not months. Roughly 1.5 years, in fact. A message sent today from the chip will arrive at the receiving station in early 2032 if the chip launched in 2030. Whatever the chip is doing right now, the team on Earth will not know about it until 18 months from now. The chip is, in a real sense, 18 months ahead of the team that built it. By the time the team learns what the chip just did, the chip has done many more things. And here, around year 5, we cross the first climax of our story. Because around year 5, The chip has done something no human probe has ever done before. It is not the first probe in interstellar space. Voyager did that. It is not the fastest probe. It already was that at minute 11. It is something else. The chip has stayed alive in interstellar space long enough for the journey to become its own kind of thing. It has crossed into a region where it is alone, no longer in our neighborhood, not yet at its destination, with no one to look at, and no one looking at it except the patient antennas back home, listening across the years. The chip in year 5 is the loneliest object humanity has ever built, and it is only a quarter of the way there. If you have stayed with the chip this far, you have already traveled further than most listeners will tonight. The journey is long, and you are walking it with care. A small action helps this channel reach others who cannot sleep tonight either. A like, a subscribe, a brief word in the comments. Thank you for being here. Let us continue. The middle years of the journey are, in many ways, the hardest to describe. Not because nothing is happening. The chip is hurtling through interstellar space at 60,000 kilometers per second. Something is always happening, at the level of atoms and dust grains and photons. But the things that are happening are very slow when compared to a human timescale. The chip's situation from year 5 to year 10 does not change in any sudden way. There is no event, there is no encounter, there is no arrival. There is only the slow accumulation of small things, day after day, year after year, deeper and deeper into the dark. This is, in some ways, the part of the story that no science fiction story has ever quite told. Because science fiction, by its nature, needs events. It needs encounters. It needs aliens or pirates or storms or something. Real interstellar travel, at least the kind we can actually build, contains almost none of those things. It contains hydrogen atoms. It contains dust grains. It contains the very faint background of cosmic rays. And it contains the chip, alone, going on. Let us try to picture what the inside of the chip looks like at year 7. The little camera is still there. The little computer is still running. The little battery is slightly more depleted than it was at launch, but only slightly. The communications laser is still functional, but the surfaces of the chip are no longer pristine. The sail, in particular, has accumulated by this point hundreds of small dust impacts. Each one has left a tiny crater. None of those craters is dangerous on its own. But cumulatively, the sail's reflectivity has been reduced by some small percentage. The sail does not look quite as bright as it did at launch. The communications laser, still aimed back at Earth, is whispering across 1.5 to 2.5 light years of distance. The signal arriving on Earth is, by this point, extremely faint. The receivers on Earth have been upgraded several times during the years of the journey, because the original receivers, built before launch, were never quite good enough for the later years. This is one of those small, often unappreciated parts of the project. The receivers on Earth have to be improved during the mission. The chip cannot be improved during the mission. The chip is frozen in 2030's technology, or 2040's technology, or whatever year it was launched in our story. The ground equipment, on the other hand, can be replaced, upgraded, expanded year by year. By the time the chip is in year 7, the receivers on Earth are vastly more sensitive than the ones the project originally bought. They have to be. The signal from the chip is, by then, near the limits of what is detectable at all. There is a quiet philosophical thing here that is worth sitting with for a moment. The chip will outlive its own technology. The chip will, throughout its journey, become more and more an antique by the standards of the ground-based equipment that listens to it. The engineers in year 7, looking at the chip's design documents, may already see things they would have done differently. They cannot change anything. The chip is sealed. The chip is the past, traveling at the speed of light through the present towards a future where its old design will still have to make do. By year 8, the chip is nearly 2/3 of the way to Alpha Centauri. By year 9, it is closer to 3/4. The numbers, in pure distance terms, are encouraging, but the chip is still, fundamentally, in the empty middle of the trip. The sun behind it is just a star. Alpha Centauri ahead of it is also still just a star, although growing slightly brighter year by year. There is nothing else in any direction. The chip is, at year 9, the furthest human-made object that has ever existed, by a margin of light years. There is no second place. There is nothing close. This is, by the way, the kind of milestone that is hard to celebrate. When Voyager One reached 1 light day from Earth in November of 2026, NASA marked the moment carefully. There was a small ceremony. There were articles. There were retrospectives on the program. By comparison, the chip in our story reaches 1 light day in 5.5 hours. It is one of many such milestones that scroll past during the journey. The team on Earth tracks each of them internally. But there is no ceremony. There is too much else going on. The chip has passed too many thresholds, too quickly, for any one of them to feel like an event. There is a kind of grief in long projects when no individual moment is allowed to be the moment. The chip is not allowed to have a single big day. The chip is, instead, allowed to have a long, quiet decade. Around year 10, the cumulative dust hits on the sail begin to be visible in the telemetry. The chip's onboard sensors, modest as they are, can detect small changes in the sail's response to whatever ambient pressure exists around the chip. The sail is, by this point, slightly less reflective, slightly less smooth, slightly less the perfect mirror it was at launch. The data, when assembled by scientists on Earth, looks like a slow drift in some baseline number. A drift that, when you understand what it represents, is the slow story of a great many tiny things hitting the sail over a great many years. The chip is being sanded down, not destroyed, not yet. The chip is built for this. The sail material was chosen, after years of laboratory work, for its ability to take this kind of abuse over 20 years. But the chip is older now. The chip is, by year 10, more vulnerable to a serious dust hit than it was at year 1. If a larger grain were to come along, a grain of, say, 10 micrometers across, the chip might not survive the impact. Most of the time, this does not happen. Most of the time, the chip's path through interstellar space is statistically clean. But the chip has been launched, in our story, as one of many. The reason there are many is that some of them, even the ones that survive the launch, do not survive the journey. Some of them encounter the larger grain. Some of them, somewhere in years 6 or 7 or 8, simply stop communicating. The team on Earth notices, 3 or 4 light years later, when the expected signal does not arrive. There is no funeral. There is no specific moment of loss. There is only the absence of a signal that was supposed to be there. For our chip, the one we are following, year 10 passes without that event. The chip is intact. The sail is pocked but holding. The little camera is still cold and silent, waiting for its single chance. The little computer is still ticking through its monitoring cycles. The chip is, by year 10, almost halfway through the journey it was designed to make. It is alive, and it is more alone than anything humanity has ever sent anywhere. Take a breath. Settle in. We are with the chip, and the chip is with us. It is moving still. It will keep moving. There is in this stretch of the journey a small mathematical fact that the engineers on Earth track quietly. It has to do with the rate at which the chip is accumulating damage. The local interstellar cloud, in the direction the chip is heading, has, on average, about 1/10 of an atom per cubic centimetre. The chip's frontal cross-section, the area of itself that is presented forward into the direction of travel, is small, a few square centimetres at most. The chip is moving at 6 times 10 to the 4th kilometres per second, or, in centimetres per second, about 6 billion centimetres per second. Multiply those numbers together, and you get a rough estimate of the number of hydrogen atoms that strike the chip's frontal area every second. The answer, very roughly, is somewhere in the millions. Millions of hydrogen atoms, individual atoms, slamming into the chip every single second the chip is in flight. Most pass through or are absorbed without notable effect, but over 20 years the cumulative count is staggering. The chip will be struck, in its journey, by a number of hydrogen atoms that, if you wrote it down in normal notation, would have something like 16 zeros in it. Of course, almost all of those atoms are too small to do meaningful damage individually. The chip is, structurally, very robust at the molecular level. Silicon and metal oxides do not care about hydrogen atoms, even fast ones. The chip can take it. But over 20 years, the cumulative count is real. The dust is the harder problem. The local interstellar cloud, by mass, is about 1% dust. Most of that dust is in extremely small grains, 10 to the negative, 14 kilograms or smaller. These are particles thousands of times smaller than a grain of sand. At normal speeds, they would be invisible to any sense. At the chip's speed, they are not invisible. They are, in their moment of impact, equivalent to small bullets. The estimates from the breakthrough starshot studies, written up over the late 2010s and early 2020s, gave a rough figure for the number of dust strikes the chip would receive. Roughly 1,000 particles of size, 1/10 of a micrometer, or larger per square centimetre of frontal area over the entire 20-year journey. This is a small number on any given day. This is a large number cumulatively. The sail, which has the largest frontal area on the chip, would be the most affected. The chip's small payload, partially shielded behind the sail in some designs, would be less so. There were, throughout the project's development, proposals to add additional shielding, to put a small graphite or carbon disc in front of the chip, absorbing the dust impacts before they reached the chip itself. Every gram of shielding, of course, slowed the chip down a little, because every gram took more energy to accelerate. So shielding became a trade-off. Too much, and the chip never reached the required speed in the 10-minute laser burn. Too little, and the chip might be destroyed by a single bad impact in year 14. The compromise in our chip's design was to use the sail itself as primary shielding. The sail is in front. The sail takes the impacts. The chip behind the sail is partially protected. If the sail is damaged badly, the chip is exposed. If the sail holds, the chip survives. The sail, in this sense, is not just the engine of the journey. It is the armour of the journey, both at once. By year 10, something quiet has changed about the mission. The chip is now in the second half of its journey, but in human terms, this is the long middle. The launch is a decade behind. The arrival is a decade ahead. The chip is, by every measure that matters, in the middle of nowhere. There is a particular kind of terror that does not feel like terror at first. It is not the terror of a sudden disaster. It is not the terror of a crash or a fire or a single moment of failure. It is the quieter terror of slowly losing relevance, of working on something for a very long time, only to realize that the world has, in your absence, moved on. By year 12, this terror has begun to settle over the mission, although no one in the control room would put it in quite those words. The chip is still functioning. The chip is still sending its small daily packets of data. The receivers on Earth are still picking them up. The science teams are still analyzing them. But the project itself, the thing that started in 2016 with two men named Yuri Milner and Stephen Hawking announcing it on a stage in New York, is no longer the most exciting thing in space science. Other missions have come and gone. Other discoveries have been made. The James Webb Space Telescope, which launched in 2021, has long since been retired by year 12 of our CHIPS journey, replaced by newer instruments. Mars has been visited by humans, perhaps. Europa has been drilled into, maybe. The map of the local universe has been redrawn more than once. And our chip is still flying. This is a quiet problem, because long missions in human institutions depend on continued attention. They depend on continued funding. They depend on someone, somewhere, deciding every fiscal year that the receivers on Earth are still worth running, that the science team is still worth paying, that the chip is still worth listening to. There is no law that says this attention must continue. There is no law that says when a mission lasts 20 years, its budget will survive 20 rounds of political budgeting. The mission could, in principle, be defunded at any point during the journey. If the mission were defunded in year 12, the chip would not know. The chip is the same chip it was at year 10. It is still transmitting its small daily packets. It is still pointing its 1-watt communications laser back at the Earth as best it can. But if no one on Earth is listening, the packets simply do not arrive. They pass into the receiving antennas, perhaps, but the antennas are unmanned, or pointed elsewhere, or shut down for budget reasons. The packets are lost. The chip continues to send. The chip will continue to send until its battery dies. But there is no one to hear it. This is one of the real terrors of long voyages. It is not that the chip will die. It is that the chip might be sending data into a void where no one is listening, and the chip will never know. We should be careful here not to overstate this. In our story, the mission does not get defunded. Funding continues. The receivers stay on. The science teams stay funded, even if reduced in size compared to the early years. The mission survives because it has the kind of public significance that is difficult for any government to abandon entirely. But the question hangs over every long mission. The question is real. It is part of why projects of this kind require careful institutional planning, careful succession of leadership, careful handoff between generations. The CHIPS mission is, in this sense, as much a problem of human continuity as it is a problem of physics. Take a breath. Stay with the chip. The dark is long. There is something here about the history of Proxima Centauri itself that is worth pausing on. The star that the chip is heading toward, the one specific star in the Alpha Centauri system, around which our target planet orbits, is called Proxima Centauri. It is a red dwarf. It is the closest known star to our Sun, slightly closer than its two larger companions, Alpha Centauri A and Alpha Centauri B. But Proxima Centauri was not discovered with the rest of the system. Alpha Centauri itself, as a bright point of light in the southern sky, has been known to humans for as long as humans have looked at the southern sky. It is one of the brightest stars visible from southern latitudes. It is mentioned in ancient observations going back thousands of years. But Proxima Centauri is faint. It is so faint that it cannot be seen with the naked eye in any normal conditions. It was not discovered until 1915 by a Scottish-born astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa. Innes was hunting for stars with high proper motion, that is, stars that move noticeably against the background sky over time. He found a faint red point near the Alpha Centauri system that moved together with the brighter pair. The faint point, he realized, was a companion star to Alpha Centauri A and B. He named it Proxima Centauri. The word Proxima in Latin means nearest. From the moment of that discovery in 1915 to the year 2016 when the first planet around Proxima was discovered, 101 years passed. From 2016 to 2022, when the second planet was confirmed, 6 more years. From 2022 to the launch of our chip in our story, perhaps another 20 or 30 years. From the launch to the arrival, 20 more. From the arrival to the data reaching Earth, 4 more. There is something humbling in that list. The star itself was only discovered just over a century before the planet hunting began. The planets were only discovered a few decades before our chip would launch. By the time the chip arrives at Proxima, the history of human knowledge of the star is, at most, 2 human lifetimes long. 2 lifetimes for a journey that is itself half a lifetime long. We tend to think of stars as ancient and well-known. Proxima Centauri is, in cosmic terms, a star humanity met yesterday. We barely know it. We have measured a few of its properties. We have detected some of its planets through the wobble in its light, but we have not seen those planets up close. We have not measured their atmospheres directly. We have not seen their surfaces. We are, in our current era, in roughly the position that ancient astronomers were in with regards to Mars. We know it is there. We know roughly where it is. We have made some educated guesses about what is on it. The chip we are following is, in this story, the first time humans will see a planet around another star with anything like the level of detail that even basic photography offers. That is what the chip is for. That is what the 20 years of empty space are paying for. A single brief glimpse of a place no human will ever stand. By year 14, the chip is far enough into the journey that Alpha Centauri itself, as a star in the sky, is no longer just a star. From the chip's position, looking forward, the Alpha Centauri system has begun to resolve. It is no longer a single point of light. With the chip's tiny camera, if it were turned forward, it could already detect that Alpha Centauri A and Alpha Centauri B are not one star but 2. The 2 of them are a binary orbiting each other every 80 years or so, at an average distance comparable to the distance between our Sun and Uranus. Proxima Centauri itself is harder to see from the chip's current position. Proxima is fainter than A and B by a wide margin. It is also, gravitationally, a long way from the main binary. The 2 larger stars are about 13,000 astronomical units away from Proxima, which is to say roughly 2,000 times the distance from Earth to the Sun. The chip is not aimed at the binary. The chip is aimed at Proxima specifically. The chip's trajectory was calculated years ago to bring the chip close to Proxima Centauri and to the small planet that orbits it, the planet called Proxima Centauri b. By year 15, the chip can resolve, in its tiny camera, that there is a smaller, redder point near the brighter pair. The chip has, in a sense, found its destination. The dim red dwarf, alone in its long orbit with its planets, is now visible. The chip is still moving at 60,000 kilometers per second. The chip has not slowed down. The chip cannot slow down. But for the first time since launch, the chip has something to aim at that is not just a number on a navigation computer. It has a target, a faint, small, real target growing brighter year by year. It is worth saying a few words about what it actually takes to listen to a chip from 4 light-years away. The chip's communications laser, as we have said, is rated at 1 watt. That is the power of a small night light. A 1 watt signal broadcast across 4 light-years is not just faint when it arrives at Earth, it is almost beyond detection at all. The reason it can be detected at all has to do with the precision of the receiving system. A laser beam, even a very weak one, has a useful property. It is, in principle, a coherent beam. The photons in the beam are in lockstep, all on the same wavelength, all in phase. This means that if you have a sensor that can be tuned to that exact wavelength and that exact phase, you can pick out the signal from the much greater background noise of the universe. The background of starlight, the cosmic microwave background, the random scattering from gas clouds in our solar neighborhood, all of these contribute noise that, in raw power, vastly exceeds the chip's 1 watt. The chip's signal is, by massive photons, a tiny minority. But the chip's signal is organized. The background noise is not. This means the receivers on Earth have to be exceptionally precise instruments. They have to be tuned to the chip's wavelength to within fractions of a nanometer. They have to be steered to the chip's direction in the sky to within fractions of an arc-second. They have to integrate the chip's signal over many seconds, or many minutes, or even many hours, building up the very faint coherent signal against the very strong incoherent noise. The receivers are, in this sense, more delicate instruments than the chip itself. The receivers also have to know with extreme precision where the chip is. The chip's position cannot be measured directly from Earth. The chip is too small, too far, too dim. The chip's position has to be inferred from its trajectory, calculated from the launch parameters refined by the timing of each signal that returns. The receivers point at the place where the chip is expected to be. They listen for some hours or days. They check whether a coherent signal at the chip's wavelength is detectable in that direction. If so, they have found the chip. If not, they have to adjust their pointing, search the surrounding area of sky, try again. This is, like everything in the project, a problem of patience. But in another version of this story, the receivers might have been shut down. The chip's signals might have been beaming back to an Earth that was no longer listening. The chip would not have known. The chip would have continued to do its work, faithful to its programming, faithful to its instructions from 12 years earlier, sending small packets of data into a universe where no one was tuned in. That alternate version of the story is, in some ways, the most haunting one of all. Because that alternate version of the story has actually happened in human history, in a smaller way. The Pioneer probes, launched in the 1970s, were the first human spacecraft to head outward beyond the planets. They sent signals back for many years. Eventually, the budgets were cut, the receivers were shut down, the missions were considered closed. Pioneer 10's last signal was received in January of 2003. Pioneer 11 went silent in 1995. The probes were still flying. They might still be flying today in some sense, but no one is listening. The probes have continued, in silence, into the dark. Our chip is, in our story, lucky. The receivers stayed on. The data came back. But the chip did not know. The chip never knew. The chip simply transmitted in good faith into whatever silence or attention the universe held on the other end. There is a moment in any long voyage, and perhaps this is true of any long human project, when the destination stops being abstract. For most of the journey, Alpha Centauri has been a number on a navigation computer, a point in a star catalogue, a name in a press release. It has been a destination in the way that a job offer in another city is a destination before you have actually moved there, real but not yet textured. For the chip, this moment comes somewhere around year 15. The chip's tiny camera, which has spent most of the journey turned off to save power, is brought online occasionally for navigation checks. The team on Earth, when they downlink the test images many months later, can see what the chip can see. Alpha Centauri, in the chip's view, is no longer a single bright point. It is 2 points. Then, on closer inspection, it is 2 points, and a faint third, much further from the main pair, the dim red dwarf called Proxima. Alpha Centauri. A is a star roughly similar to our Sun. It is slightly larger, slightly brighter, slightly older. Its mass is about 1.1 times the mass of the Sun. Its luminosity is about 1.5 times the Sun's. From Earth, it is the brighter of the two main components of the Alpha Centauri system, and it contributes most of the light that we see when we look at the Alpha Centauri pair with the naked eye from the southern hemisphere. Alpha Centauri b is slightly smaller and slightly cooler than the Sun, about 90% of the Sun's mass, about half of the Sun's luminosity. The two stars A and B orbit each other on a path that brings them as close as about 11 astronomical units from each other, which is roughly the distance from our Sun to Saturn, and as far apart as about 36 astronomical units, which is roughly the distance from our Sun to Pluto. Their orbital period is about 80 years. By the time the chip arrives, the two stars are in whatever configuration the calendar happens to put them in. Proxima Centauri, the third star of the system, is much smaller than either A or B. Its mass is about 1/8 of the Sun's mass. Its luminosity is something like 1/150th of the Sun's. It is, by stellar standards, a small, dim, cool star. It is a red dwarf of the spectral class called M5, 5V, which is to say it is on the cooler end of the red dwarf range. Red dwarfs are the most common kind of star in the galaxy, by a wide margin. The majority of stars in the Milky Way are red dwarfs. We just cannot see most of them from Earth because they are too faint. Proxima is also a long way from the main binary in stellar terms. It orbits Alpha Centauri, A and B, from a distance of roughly 13,000 astronomical units. That is about 1/5 of a light year. Proxima takes, very roughly, 500,000 years to complete one orbit around the binary pair. Whether Proxima is gravitationally bound to the system at all, in the long term, is a question that astronomers have argued about for decades. Recent work suggests that Proxima is bound, but only loosely. Proxima is, in a sense, the lonely sibling of the system, far from the main pair, faint, long forgotten until 1915, and around Proxima 2 planets orbit. They are called, in the catalogue of exoplanets, Proxima Centauri b and Proxima Centauri d. The first of these, Proxima Centauri b, was discovered in 2016. The work was led by an astronomer named Guillem Anglada Escudé, working with a team based at Queen Mary University of London. The team had been looking for several years before the discovery at very slight variations in the light from Proxima. The variations, when analysed carefully, suggested that something was tugging on the star. Something with a mass at least 1.3 times the mass of the Earth in an orbit of about 11.2 days, at a distance of about 0.05 astronomical units. That distance is, in absolute terms, very close, about 1/20th of the distance from our Earth to our Sun. But Proxima is much cooler than our Sun, and so a planet at 0.05 astronomical units from Proxima receives an amount of starlight that is, very roughly, comparable to what Earth receives from the Sun. Not the same, but comparable. The planet, in 2016, was announced to be in what astronomers call the habitable zone of its star. The habitable zone is the range of orbital distances at which liquid water could in principle exist on a planet's surface. The phrase has become famous in popular science writing. It has also become, in some ways, misleading. Being in the habitable zone is not the same as being habitable. A planet in the habitable zone has the right amount of warmth, in principle, but it must also have an atmosphere. It must also have water. It must also be protected from the radiation of its star. Proxima Centauri b satisfies the warmth condition very roughly. Whether it satisfies the others, we do not know. The second planet, Proxima Centauri d, was confirmed in 2022. The team that confirmed it was led by João Faria, working with European Southern Observatory data, using a high-precision instrument called ECES at the Very Large Telescope in Chile. Proxima d is smaller than Proxima b. Its minimum mass is roughly 1/4 the mass of Earth. It orbits Proxima even closer than Proxima b does, with an orbital period of only about 5 days. It is almost certainly too close to its star and too small to hold an atmosphere of the kind that would matter for any conventional definition of habitability. But the discovery of Proxima d mattered for a different reason. Until 2022, it was reasonable to wonder whether Proxima b was a one-off, a single planet around a single star, perhaps an accident of formation. The detection of a second planet around the same star showed that planet formation around Proxima had produced at least 2 real bodies. The system around the lonely red dwarf was not empty. It was, in some quiet way, a system. There may be more. There was, for a while, evidence of a possible third planet, Proxima Centauri c, in a longer orbit of about 5 Earth years. That detection has been disputed. Some teams claim it is real. Other teams claim the signal is an artifact. The honest answer, as the chip approaches the system, is that we do not yet know the full inventory of bodies around Proxima. Our chip will not be able to give us that full inventory either. The chip is aimed at Proxima Centauri b, the close-in, potentially habitable world. The chip has, in its mission profile, the goal of making a single brief observation of that one planet. Other planets, if they exist, will not be on the chip's path. Take a breath. The chip is now close. The system is in front of it. The destination is, for the first time, a real place rather than an abstract number. By year 17, Alpha Centauri A and B, in the chip's view, are no longer points of light. They are small bright disks, slightly resolved. The chip's tiny camera is not a great telescope, but at this distance the 2 main stars are bright enough and large enough that some structure can begin to be detected. Sunspots, perhaps, if the chip's camera were sensitive enough. Some faint corona around each star, probably not visible at the chip's resolution. But the disks are there. Proxima Centauri, by year 17, is also a small disk. A red disk. Much smaller and dimmer than its companions. But the chip is approaching Proxima, not A or B. The chip's path takes it close to Proxima specifically. The chip is on a trajectory that, if it had been calculated to take the chip past Alpha Centauri A or B, instead, the chip would be in a very different part of the sky right now. As it is, the chip is aimed at the lonely red sibling, the dim one, the one Robert Innes only found in 1915. By year 18, the chip is close enough to Proxima that the star is bright in the chip's view. The chip can begin to detect the planet Proxima Centauri b in some of its measurements. Not as an image, not yet. The planet is too small. The chip is still too far. But the planet's gravitational signature, the slight wobble it imparts on Proxima, is now detectable in the chip's instruments. The chip is, in a small way, doing the same kind of work that Anglada Escudé and his team did from Earth in 2016. The chip is, in real time, confirming that the planet is where the Earth-based observations said it would be. By year 19, the chip can begin to image the planets directly. The chip is, by this point, only a few months from its closest approach. The numbers, the planning, the years of empty space, All of it is converging on the single window of seconds during which the chip will pass by Proxima Centauri b at speed and take whatever data it can. There is a quiet anticipation in the control room on Earth, even though the team will not know what the chip is seeing for many years yet. The signals from the chip in year 19 are about flight conditions 4 years earlier, near year 15. The team in 2050 is reading data from 2040. Whatever the chip is doing right now, today, in year 19 of the journey, the team will not see until somewhere in year 23. Time on this voyage is no longer one thing. Time on Earth, time on the chip, time of arrival at Proxima, time of arrival of the signal back home. These are 4 different times, separated by years. The mission, in its final stretches, is happening simultaneously across all of them. At 60,000 kilometers per second, the chip enters the Alpha Centauri system. There is no boundary, of course. There is no line in space marked Alpha Centauri system begins here. The transition is gradual. The light of Proxima, which has been growing year by year, is now the dominant light source in the chip's view. The stars behind the chip, including the Sun, are no longer special. They are background. The chip's instruments, designed for this single window, are powering up. The little camera is on, fully on for the first time. The little spectrometer, if the chip has one, is active. The little magnetometer is reading the local magnetic field of Proxima's neighborhood. The communications laser is preparing to transmit, in real time, whatever the chip is recording. The chip is approaching Proxima Centauri b, the planet. As the chip closes on it is a small reddish world. It is roughly Earth-sized, perhaps slightly larger. Its mass is at least 1.3 times the mass of Earth. It orbits its star every 11.2 Earth days. That is its year. 11 days. A year on Proxima b is shorter than the typical menstrual cycle, shorter than 2 work weeks. The planet completes one full circuit of its star in the time most people on Earth pay one rent or finish one paycheck. The whole experience of seasons on a tidally locked planet at this orbit would be unrecognizable to anyone from Earth. Tidal locking is the term astronomers use for what happens when a planet is so close to its star that the same side of the planet always faces the star. Like our moon, which always shows the same face to Earth. Proxima Centauri b is very likely tidally locked. We are not absolutely sure. The honest answer is that planets in eccentric orbits, with certain configurations, can avoid full tidal locking and instead settle into a spin-orbit resonance, like Mercury does around our Sun. But the most likely state for Proxima Centauri b, based on current models, is full tidal locking. One side of the planet always faces Proxima, one side always faces away. If the chip can resolve the planet, even briefly, what the chip will see is 2 very different halves of the same world. The day side, baked by the constant low-energy red light of Proxima. The night side, never warmed by direct starlight in any of the planet's history. Between them, a narrow band, the terminator, where the star sits permanently on the horizon. If life exists on Proxima Centauri b, many astronomers have speculated it would exist along this terminator band in the eternal twilight where temperatures might be moderate. But here is the part that has to be said honestly. We do not know if there is life there. We do not know if there is liquid water there. We do not know if there is an atmosphere there at all. As of this writing, Proxima Centauri b is a planet we have detected by its gravitational tug on its star, and almost nothing more. The chip we are following will, in a single passage of seconds, gather more direct information about Proxima Centauri b than all human astronomy has gathered since the planet's discovery. There is also Proxima itself. Proxima Centauri is a flare star. This is not a small detail. Red dwarfs of Proxima's type are known for producing violent outbursts of radiation, called flares, that briefly increase the star's brightness by huge factors. On the 1st of May 2009, a team of astronomers using 9 telescopes, including the Atacama Large Millimeter Array in Chile, recorded a particularly powerful flare from Proxima. During the flare, the star's ultraviolet brightness, as observed from Earth, increased by a factor of approximately 14,000 times its normal brightness. In a matter of seconds, the flare lasted only briefly, but the energy released was enormous. There was an earlier event in 2016, observed by an array of small telescopes called the Everiscope. During that flare, Proxima briefly became, for a few seconds, bright enough to be visible to the human eye from a dark site on Earth. Normally, Proxima is too faint to see with the naked eye. For those few seconds in 2016, it was not. More recently, an ALMA survey published in 2025 reported 463 separate flare events from Proxima, over a total of about 50 hours of observation. That is roughly 9 flares per hour. Some of them small, some of them very large. The largest one in that survey was about 1,000 times brighter than Proxima's normal output. This is the environment in which Proxima Centauri b sits, a planet very close to a star that erupts on average several times per hour. Some of those eruptions are mild. Some of them are enormous. The radiation in the largest flares would be devastating to anything resembling Earth life on the planet's surface, unless that life were protected by a substantial atmosphere or by some other shielding. Whether such an atmosphere exists, we do not know. The chip, in its single passage, may be able to detect signatures of an atmosphere in the planet's spectrum, if there is one to detect. The chip may also pass while Proxima happens to be flaring. The chip may be partially damaged by the flare, depending on its intensity. Most likely the chip will survive because the chip is small and the flare's energy will be brief. But it is one more risk in a journey full of risks. It is worth pausing on what an atmospheric signature would actually look like in the chip's data, because this is the kind of result that, if it comes, will be the headline result of the entire mission. When light from Proxima reaches the chip after passing through whatever thin envelope Proxima Centauri b might have, certain wavelengths are absorbed by the atmosphere's molecules. Different molecules absorb different wavelengths. Oxygen absorbs at certain specific bands, water vapor at other bands, carbon dioxide at others again, methane at others. The chip's spectrometer, if its design includes one capable of this, would record the light coming through the planet's atmosphere during the brief window of the flyby. The light would have small notches in it, specific dark bands at specific wavelengths. Each notch, when analyzed, would correspond to a specific molecule. If the chip detects water vapor bands, that would not prove liquid water on the surface. It would prove water vapor in the atmosphere. Those are not the same thing. If the chip detects oxygen, that would not prove life. It would prove oxygen, which on Earth happens to come from life, but on other planets can come from other processes. The chip's data, in other words, would not be a yes or a no answer to whether Proxima Centauri b is habitable. It would be a list of which molecules are there and which are not, and in what rough proportions. The interpretation, the meaning, would take years of analysis by teams of scientists on Earth after the data arrived. This is, by the way, one of the reasons the mission is patient. The chip cannot answer the question by itself. The chip only gathers the data. The data is the beginning of an answer, not the answer. The chip flies, and observes, and transmits. The answer is built slowly over time by humans looking carefully at what the chip recorded. The closest approach happens in a window measured in seconds. The chip, travelling at 60,000 kilometers per second, will pass within some calculated distance of Proxima Centauri. The exact distance depends on the navigation precision of the launch, which is itself a function of the laser array's pointing accuracy, the sail's stability during acceleration, the chip's drift across 20 years, and the trajectory of the planet at the moment of arrival. The mission planners have aimed for as close a flyby as possible, while still allowing the chip's instruments to function. The exact number varies in different versions of the mission concept, but the useful observation window, when the planet is large enough in the chip's field of view to be photographed and analyzed, is measured in seconds, not minutes. Let us be careful here, because this is the climactic moment of the entire mission, and it must be told accurately. The chip has been traveling for 20 years to reach this moment. During the moment itself, the chip is doing what it was designed to do. The little camera is taking images, as many images as its storage and processing can manage in the few seconds available. The little spectrometer is recording the spectrum of light from the planet, looking for signatures of atmospheric composition. The little magnetometer is recording the local magnetic field. The little computer is processing all of this data, compressing it, packaging it, preparing it for transmission. The communications laser begins to transmit, almost immediately, what it can. The chip cannot wait. The chip is already past the planet in a fraction of a minute. The chip is already heading away into the deeper system, out toward whatever is on the other side. The chip has, at most, a few minutes of close observation. After that, the planet is receding behind the chip, the distance growing again. The chip continues to gather what it can, but the resolution of its images, the strength of its signal, the value of its data, all of those things peak in the few seconds around closest approach. The whole climactic event of the mission lasts less time than this one paragraph of narration. 20 years of travel. A few seconds of useful observation. Then the chip is gone. This is the strange, almost cruel mathematics of a flyby mission. The arrival is not, in any traditional sense, an arrival. The chip does not land. The chip does not orbit. The chip does not even slow down. The chip passes through the system like a stone through a pond. It makes its observations in the instant of passing, transmits what it can, and then continues on its trajectory, into the dark on the far side. Within a single hour of the closest approach, Proxima Centauri b is far behind the chip. Within a day, the entire Alpha Centauri system is a region of stars in the chip's rear view. The chip continues to transmit, sending back the data it gathered during the flyby. The transmission will continue for as long as the chip has battery and the chip has trajectory that still points back at Earth. But the chip itself is moving away from Earth, now at the same 60,000 kilometers per second that brought it here. The chip is, from the moment of closest approach onward, on its way out of the Alpha Centauri system entirely, on a path that will take it into the interstellar dark on the far side of Proxima. The signal from the closest approach, transmitted at the speed of light, takes 4 years and 3 months to reach Earth. By the time that signal arrives, the chip is already an additional 2.5 light-years past Proxima, deeper into the unknown. By the time the team on Earth reads the chip's photographs of Proxima Centauri b, the chip has been gone, in a sense, for years. The chip in the photographs is not the chip the team is reading from. The chip in the photographs is a moment frozen in the data. The chip that exists today is somewhere else, doing something else, beyond reach. Let us slow down for a moment on the geometry of the flyby itself, because this is the moment the title of our story has been pointing toward, the moment when the chip actually arrives at Alpha Centauri. And the geometry of arrival at this speed is unlike anything the human imagination has ever needed to picture before. When a spacecraft from Earth arrives at one of our own planets, like Mars or Saturn, or Jupiter. The spacecraft slows down. Cassini took several hours to enter Saturn's orbit, gradually adjusting its velocity using gravity assists from moons, finally settling into a stable path around the planet. Voyager One and Voyager Two, by contrast, did not slow down at Jupiter or Saturn. They were flyby missions. They passed each planet in a window of hours, gathering data, then continued onward. Voyager's flybys, though, were at speeds of a few tens of kilometers per second. The probes were close to the planets, in their hour or two of close approach, but they were also moving slowly enough that the planets had time to be photographed in detail. Our chip is moving at 60,000 kilometers per second, 3,000 times faster than Voyager's flybys. Whatever Voyager could photograph in 2 hours, our chip has to photograph in 2.5 seconds. Or, more accurately, our chip has to photograph in whatever fraction of a second the planet is actually large enough in the chip's field of view to register. The chip's camera, in any practical design, has a small angular resolution. The chip's optics are constrained by the chip's mass. A larger camera would be a better camera, but a larger camera means more grams, and more grams means slower acceleration during the laser burn. The compromise, in the studies, is a camera with an angular resolution somewhere comparable to a small handheld telescope on Earth. Good enough to resolve a planet at close range, not good enough to map its surface features in detail. The window during which Proxima Centauri b is at maximum apparent size in the chip's view depends on the chip's closest approach distance. If the chip passes within, say, a few 100,000 kilometers of the planet would be in close range for perhaps several seconds. If the chip passes within a few million kilometers, the planet would be a distinct disk, briefly, in the chip's view, for less than a minute. If the chip passes within a few tens of millions of kilometers, the planet would never be more than a faint dot, even at closest approach. The mission's success depends on aiming accurately enough to bring the chip within an acceptable distance. The aiming is, like everything else, hard. The chip was given its trajectory by the laser 20 years before arrival. The laser had to point not at where Proxima Centauri b was at the time of the burn, but at where Proxima Centauri b would be 20 years later. The planet orbits its star every 11.2 days. In 20 years, the planet makes more than 650 complete orbits. The aim has to be accurate to within the planet's orbital motion at the moment of flyby, accurate to within seconds of timing across a 20-year gap. This is the kind of precision that requires very careful astronomy in the years leading up to the launch. The team has to know Proxima's exact position, exact velocity, exact ephemeris with extreme accuracy. The team also has to know Proxima Centauri b's exact orbital parameters with similar accuracy. Both numbers will be refined over the years of the chip's flight by ongoing observations from Earth. The chip will receive no course corrections because the chip has no thrusters. But the team on Earth will know, by year 19, exactly where the chip is going and exactly where Proxima Centauri b will be when the chip gets there. If the navigation is off, the team will know months in advance and there will be nothing to do about it. If the navigation is correct, the chip will pass within its target distance. The camera will catch its frames. The spectrometer will catch its light. The data will be assembled, compressed, transmitted. The whole event will be done before the chip has time to register that it has happened. The chip will then move onward into the far side of the system, gathering whatever decreasing data it can as Proxima recedes behind it. The data, when it arrives on Earth 4 years later, will be the answer to a question humans have been asking, in one form or another, since long before there was a science of astronomy. The question is simply, what does a planet around another star look like when you actually see it, not in a model, not in a theoretical paper, in a photograph. The answer, in our story, fills several gigabytes of the receiving team's storage. The first image is processed and posted on the project's internal site, then released to the public after a brief vetting period. The image is, in technical terms, not very impressive. It is grainy. It is small. It is, by the standards of the photographs we have of Mars or the Moon, primitive. But it is the first such image of a planet around another star, taken at close range. The image will be on the front page of every newspaper that still has front pages that morning. The planet in the image looks small. It looks reddish. The day side and night side are, perhaps, visible as a sharp boundary across the planet's face. There is, perhaps, a slight bluish tint along one edge, which could be an atmosphere, catching the light of Proxima at the planet's limb. There is no obvious sign of life. There is no obvious sign of vegetation. There is no obvious sign of intelligent activity. There is, instead, the same kind of quiet, ordinary, alien beauty that any rocky world has when seen from close enough. Just a place no one has ever stood, a place no one is likely ever to stand. That, in the end, is what the journey was for. Not for a definitive answer to whether there is life on Proxima Centauri, B. Not for a definitive answer to whether the planet is habitable. Those questions will require missions far beyond what our chip can do. Our chip's gift is something smaller and more profound. The chip has shown us what the planet looks like from up close. With direct light, the planet has been seen, and the chip itself is, by the time we see what it has shown us, long past, long gone. Moving outward into the deeper dark, the chip is gone, past the system, but its signal is still traveling. Light, even from this close a star, takes 4 years and 3 months to cover the distance. That number, 4.24 light-years, has been the central number of this entire story. It is the distance from our Sun to Proxima Centauri. It is also the time the chip's signal needs to come home. For those 4 years, the data exists in transit. It is, in a literal sense, in flight. Photons, encoded with the chip's recordings, are sailing through interstellar space at the universe's only top speed. The data has left the chip. The data has not yet reached the Earth. The data is, during those 4 years, nowhere and everywhere at once, depending on how strictly you define location. This is a real fact, not a metaphor. The information about whether Proxima Centauri b has an atmosphere, whether the chip detected water signatures, whether the planet's surface showed anything that could be a hint of life, all of that information exists. It exists in the form of light traveling toward Earth, but no one on Earth can read it yet. The information is, in a sense, real but unreachable. By the time the signal arrives, the project belongs to different people than the ones who began it. Some of the original engineers are retired. Some have moved to other work. Some have passed. Many are still there, older now, slower now, watching the antennas with their grown children beside them. The lead engineer who, 24 years ago, signed off on the laser calibration is now in her 60s. The intern who, 24 years ago, calibrated the chip's communications laser is now the senior project lead. The president of the country that originally funded the mission is 2 presidents ago, or 3. This is, by the way, the Voyager pattern. NASA's Voyager team has long included engineers in their 80s who advise on specific subsystems and team members so young that their parents had not yet been born when Voyager One launched in 1977. Long missions live across generations. They have to. There is no other way for them to survive. Our CHIPS project, in our story, will live across the same kind of intergenerational handoff. It will not be the same group of people at the end as at the start. It will be in some ways an entirely new institution. But the institution will have been continuous. The mission will have been one mission. The chip will have been one chip. When the signal does arrive, in year 24 of the mission, the receiving antennas are ready. They have been listening for years for the slightly stronger pulse that means the chip is sending its main archive. The signal, when it comes, is faint. 1 watt, broadcast across 4 light years, attenuated by the cube of the distance, arrives on Earth as a whisper. The receivers integrate the signal over many hours, even days, building up the chip's data byte by careful byte. The first images of Proxima Centauri b emerge from the data slowly, over weeks. They are not the clean, beautiful photographs that human imagination might expect. They are pixelated. They are dim. They are oriented at strange angles, because the chip was tumbling slightly during the flyby, and the team has to reconstruct what the chip was looking at in each frame. But the images are real. They show, for the first time in human history, a planet around another star, photographed from close enough to see something. A reddish surface. A possible atmosphere, perhaps. Some hint of differentiation between day side and night side. Some hint of structure. The team in the control room, in year 24 of the mission, is mostly silent when the first clear image appears. There is, in some of the eyes, the same kind of tears that were there at launch. But these tears are different. The launch tears were about anticipation. These are about something that, for some of these people, has taken the better part of their careers to bring home. The chip itself, in year 24, is not in the photograph. The chip is somewhere on the far side of the Alpha Centauri system, traveling outward at 60,000 kilometers per second, still transmitting back whatever it can detect of the receding system. The chip is, by the time its photographs are read on Earth, already a quarter light-year past Proxima, deep in unmapped space again. The chip is no longer near anything. The chip has another star ahead of it, somewhere, but the chip will not reach that star in any time the chip can survive. The chip will simply continue. The chip will continue for, in principle, as long as anything can. Take a breath. Settle in. We are near the end of the road, although the chip is not. There are people in the receiving room, in year 24, who were children when the project was announced in 2016. There are people who were not yet born when the laser fired. There are people who, in 20 years more, will be retiring from the mission, handing it over to a new generation, the way they themselves received it from those who came before. The mission is, in this sense, the longest single conversation humans have ever held with a single object. The chip has been listened to, by some team or another, every working day for almost a quarter of a century. The chip has answered, in its small daily packets, every working day for the same period. The relationship between the chip and the Earth team is the longest one-way friendship in human history. The chip cannot hear them. The chip can only speak, and the team can only listen. But the listening has been continuous, generation to generation, for nearly 24 years. That is, in some ways, the real terrifying part of the voyage to Alpha Centauri. Not the distance, not the engineering, the patience. The slow handoff of a single project across human time, longer than most careers, longer than some marriages, longer than some governments. The kind of attention that, for a long time, no human institution was able to sustain. The chip, in its quiet flight, has demanded of us a kind of focus we had to learn how to do. The signal has come home. The chip has not. The chip is not done. The chip will not be done for a very, very long time. After the flyby, the chip continues. Its battery, The slow radioactive decay of a small amount of fuel inside it has many decades of life remaining at the time of arrival. The chip continues to transmit. Whatever data it gathers in the years after the flyby, the chip sends back, packet by patient packet. The signal arrives at Earth between 4 and 5 years after each moment of transmission. The signal will keep arriving until the chip's battery finally falls below the threshold needed to power the communications laser. After that, the chip will continue to fly, but it will no longer speak. It will become silent. It will become, in a way, an artifact rather than an instrument. But the chip's flight does not end with its voice. The chip continues onward deeper into the galaxy, on the trajectory the laser gave it 20 years and 4 years ago. The chip cannot turn. The chip cannot stop. The chip will move at 60,000 kilometers per second for, in principle, the rest of its physical existence. The numbers, when you look at them, are humbling. In 1,000 years, the chip will be roughly 190 light-years past Proxima. In 10,000 years, it will be nearly 2,000 light-years out. In 100,000 years, the chip will be deeper into the galaxy than the human race has ever seriously imagined sending anything. The Voyager probes, which are similarly on permanent escape trajectories, are projected to encounter other stars only after time spans of tens of thousands of years. Voyager One, for example, is expected to pass within about 1.7 light-years of an obscure star called Gliese 45 in roughly 40,000 years. That is, by the way, a stellar passage that will see Voyager remain a long way from the star, never actually getting close enough to be captured by it. The chip in our story, on its own trajectory, will pass through similar gaps in similar deep time. Stars will come into its general vicinity, separated by light years. The chip will continue past them. The chip is, in this very long view, not a probe at all. The chip is a slowly traveling piece of human history, hurled outward by the most powerful laser ever built, fated to drift through the Milky Way for as long as the Milky Way itself exists. There is something quiet and oddly comforting in this. The chip will outlive the mission. The chip will outlive the receivers on Earth that listened to it. The chip will outlive the antennas, the buildings, the institutions, the languages, the names of the engineers who built it. In 10,000 years, every detail of the chip's mission, written in human records, will have changed beyond recognition or been forgotten entirely. But the chip itself, the physical chip, will still be moving, still on the same trajectory the laser gave it. In 1,000,000 years, the chip will be far enough into the galaxy that, statistically, it might pass through some interstellar dust cloud denser than anything our solar neighborhood currently contains. The chip might be damaged in such a passage. The chip might be slowed slightly by gas resistance, although the effect would be small. But unless the chip happens to collide with something solid, which is extremely unlikely in interstellar space, the chip will continue. The probability of the chip colliding with anything large enough to destroy it in any given period of time is so small that the chip's lifetime is measured not in years or millennia, but in some vastly longer scale set by extremely rare statistical events. The chip might, in the deepest of times, encounter another civilization. We do not know if such civilizations exist. We do not know, if they do, whether they would notice such a small object. The chip is a gram of metal. It is not advertising itself. It is not transmitting any signal that another civilization could intercept from a distance, because the chip's communications laser is aimed specifically at Earth, and once the battery dies, the chip is dark. The chip is, for any practical purposes, lost the moment its voice fails. But the chip exists. The chip is, in a way that almost nothing humans have ever made, is permanent. The chip is a thing that humanity has put into the universe, and the universe will keep it. Take a breath. Let your shoulders settle. We are nearly at the end of our walk. There is a small, almost private thing that should be said here at the very end. The mission we have followed tonight is not a confirmed mission. The Breakthrough Starshot project, announced in 2016 by Yuri Milner and Stephen Hawking, is a research initiative. It is a study. It is a 100 million effort to determine whether such a journey is even possible, given the engineering challenges. There is no fixed date for the launch. There is no certainty that any chip will ever actually fly. Many physicists who study the problem think the laser array required is so far beyond current technology that a true Starshot launch will not happen this century. Many others think it might be sooner. The honest answer is that we do not know. But the proposal exists. The papers have been written. The materials have been tested in laboratory chambers. The mathematics has been verified, scrutinized, criticized, defended. The journey we have walked tonight is, at this moment, a journey on paper. The chip exists in the calculations. The laser exists in the drawings. The arrival at Proxima Centauri, B, exists in the simulations. Whether the journey actually happens, in some real century yet to come, depends on choices that the people who run our institutions have not yet made. It depends on funding. It depends on engineering. It depends on the slow, patient process by which an audacious proposal becomes a tested prototype, becomes a small experiment, becomes a real mission. The Voyager probes were imagined for years before they flew. The Webb telescope was proposed in 1996 and did not launch until 2021, 25 years later. Big projects move slowly. The chip we have followed tonight may yet move slowly into being. But here, in our minds, tonight, the chip has flown, the laser has fired, the journey has been made, the signal has come home. The gram of metal we have followed is, in our imagination, somewhere past Proxima Centauri tonight. It is moving. It is alone. It is silent now because its battery is failing, but it is still moving. There is no one near it for thousands of light years in any direction. There will not be, for any time scale that the human mind can comfortably hold. The chip is, in its small way, a piece of our species that has gone where we could not go ourselves. If you have walked all the way to the edge of this story with the chip, thank you. 24 years is a long time, even in a story. The journey we have walked tonight is, in some ways, the slowest journey humans have ever planned. Slow, not because the chip moves slowly, but because the road is so long that even at 1/5 the speed of light, it takes most of a working career to cross. This channel exists, in part, to walk these long roads with you on nights when sleep is slow to come. If the journey tonight gave you something, a quiet moment, a settled breath, a thought to carry into the dark, please consider liking the video and subscribing. It helps this channel keep making these journeys. It helps other people who cannot sleep find their way here. It costs nothing and means a great deal. The chip in our story is somewhere in our imagination tonight, still flying. The laser, in some real future we cannot yet see, may yet fire. The voyage to Alpha Centauri may yet, in real engineering and real time, become a real thing rather than a thing on paper. Whether that happens depends on choices our descendants will make. It does not depend on us. It depends on people we will never meet. But in the meanwhile, tonight, the chip flies in the only place it currently can, in our minds, in our imaginations, in the strange quiet space where physics and patience meet, and where the universe seems for a moment both larger and more reachable than it ordinarily does. Settle in. Let your shoulders drop. The chip is moving, still, in the long dark. Right now, in your room, in your bed, the chip in our story has not yet been built. The laser has not yet been fired. The journey has not yet begun. And yet, in our imagination, it is already arriving. The future of this mission and its past sit, tonight, in the same quiet room as you. The gram of metal keeps going. There is no one to tell. There never will be. And somewhere, very far ahead, the next star is already waiting,